We've all heard of ice ages, but why do they actually happen? Why does our nice planet, which is just the right temperature, repeatedly turn all chilly only to warm back up again? Well, to try to answer that question, we need to start by looking at the data. This graph shows how the Earth's temperature differed from its current average value over the last 500,000 years, and we can see a clear distinction between the ice ages, which are the dips here, and the interglacial periods between the ice ages, which are the peaks. Not only that, but the temperature seems to move around slowly most of the time, and then suddenly jump out of an ice age and back into one, where we see these very steep bits on the graph. And they appear to be occurring roughly every 100,000 years. Now, the Earth's orbit around the Sun does vary slightly over long periods of time, which affects how much of the Sun's energy reaches us, and this can explain some of what we see here. But if that were the only thing going on, we would expect the temperature to slowly move around within a narrow range. It doesn't explain why the temperature changes are so large and so sudden. To figure that out, we need to do some maths. Here we have the Sun and the Earth, obviously not to scale, and when light from the Sun reaches Earth and hits land or water, around 10% of that light is reflected away, and the rest is absorbed. This is because water and land are good at absorbing solar radiation, and they're said to have a low albedo. On the other hand, if that light hits snow or ice, around 80% of it is reflected because they have a much higher albedo. So the total energy absorbed by Earth per second is given by pi r squared, that's the area of the shadow of the Earth, so how much light hits it, times Q, the power of the Sun's radiation, times 1 minus A, the Earth's average albedo, to account for the energy which is reflected away. However, the Earth's albedo isn't constant. Since it's affected by the amount of ice covering the Earth's surface, it depends on temperature. And it's reasonable to assume that at very low or very high temperatures, a small change to the temperature won't affect the albedo that much. For instance, if there's already lots of ice, it's difficult for more to accumulate. And if there's very little ice, there isn't much which can melt. In between the two extremes, however, we would expect it to be far more sensitive to any change in temperature, which suggests the graph of albedo versus temperature should look something like this, which we call a sigmoid function, because it looks a bit like a letter S, or a Z in this case. The Earth's albedo takes a long time to reach equilibrium though, since it involves huge glaciers forming and melting. So, in fact, we need a differential equation to describe how the albedo evolves over time, constantly moving towards its steady-state value for the current temperature, which we'll call A star. Now, to balance the energy being absorbed from solar radiation, the Earth also emits energy, which is given by the Stefan-Boltzmann law. This says that the power emitted is equal to 4 pi r squared, the surface area of the Earth, times the Earth's emissivity, times the Stefan-Boltzmann constant, times its temperature to the power 4. But the key part here is that T to the power 4. None of the other parts are going to change, only the temperature. Now, it is true that some of the emitted energy is reabsorbed by greenhouse gases in the atmosphere, so the concentration of these gases does play a part, but it isn't nearly as significant here as it is in the context of global warming and climate change, so for simplicity, we'll ignore that for now. And now that we have expressions for the power being absorbed and emitted, we can simply write a differential equation for the Earth's temperature. Here C is the heat capacity of the Earth's atmosphere, so how much energy it takes to heat it up. And this equation simply says that if more energy is being absorbed than emitted, then the Earth heats up, and if it's the other way round, then it cools down, as we'd expect. The Earth's temperature reaches equilibrium much quicker than its albedo does though. In fact, it only takes months as opposed to thousands of years. And since we're looking at very long timescales here, we can assume that the temperature is always in its steady state. This is called the pseudo-steady state hypothesis, and it's a very useful technique for simplifying a system when you have variables that evolve at very different rates. And the final part of our model, the driving force of the system, are these variations in the Earth's orbit, called Milankovitch cycles. Over hundreds of thousands of years, the eccentricity of the Earth's orbit changes. This animation is exaggerated, but it goes from circular to a more stretched ellipse and back again. and the tilt of the Earth's axis of rotation goes through a cycle every 41,000 years. There are a few other cycles too, but they all just very slightly alter how much solar energy different parts of the Earth receive at different times of the year. So finally we can see what behaviour our model predicts depending on the value of Q, the solar radiation. Firstly, if Q is low, then the emission and absorption curves only meet in one place, which corresponds to a steady state with a low temperature. Now, if the green line is above the red line, that means more energy is being emitted than absorbed, so the Earth cools down, and we move to the left. Similarly, if the red line is above the green line, we'll move to the right. So, just as we'd hope, this steady state is stable and would correspond to the Earth being in an ice age. Next we have the case where Q is somewhere in the middle, and here there are 3 steady states, the low one as well as 2 new ones. Here the 2 outer ones are stable, so the temperature is attracted towards these values, and the middle one is unstable. Finally, when Q is large, we again have just one steady state, this time at a much higher temperature. This is still stable, and would represent the Earth being in an interglacial period. Now, a slightly more helpful way to visualize this system is to plot the steady states on a graph of Q versus temperature, where the solid lines are the 2 stable steady states, and the dashed line is the unstable one. And if we run a simulation, where we start off with Q being at its lowest value, and see how the system evolves, we can see a really cool pattern emerge. The temperature only moves slowly while the low steady state exists, then it quickly jumps up to the higher branch. But then it doesn't return to the lower branch until Q has decreased much further. This behaviour, where the temperature lags behind the changes in the driving variable, Q, is called hysteresis. And as we can see, it means that undoing a small change in Q won't necessarily cause the temperature to retrace its previous steps. And this is because of the albedo, which acts to keep the Earth warm when it's warm, or cool when it's cool. And if we switch to an animation where we also have a graph showing how each of the variables evolves over time, it helps us to understand how the variables respond to one another. The albedo essentially just jumps between 2 values, and when it does, the temperature jumps as well. But in between these jumps, it only moves very slowly, which is exactly what we saw in the data back at the beginning. So there we have it. The results from our model match what we saw in the data. So while we could use a more complex model with more variables included, this gives a really good explanation of the underlying forces that cause ice ages to happen. That's all for this video. As always, if you'd like to see more videos like this, please subscribe, or if you have any suggestions for things you'd like to see in future videos, please pop them in a comment. Thanks for watching, and I'll see you next time.